Okay, so we could say that everything we've done this semester has led up to this day, today. So, good that you came. We're using everything from all semester to make a really important conclusion. So let's get started. Here we go. So, be more awake than the first class. Okay? So these two graphs that I'm showing you here relate to, we saw this maybe 2 months ago, and these relate to the accumulation of weight. So suppose there's like a truck, okay, and it's dumping something, and there's a scale that's measuring the weight as time goes by, as the stuff gets dumped on, okay? So it's accumulation of some weight, and this is in, say, I don't know, pounds and seconds or something like that. So I want you to just talk with the person next to you and make sense of what are you seeing in these two graphs? What does the left graph represent? What does the right graph represent in the context of a weight quantity that's accumulating over time? Okay, so go. So talk to the person next to you. Okay, are we still talking about these graphs? Yeah, sure. How about Jeff? Tell me any one thing, just one thing about what you're seeing. We have constant rate of change. Agree with that? Adria, is there a constant rate of change here? Or can you maybe be more specific? What's the constant rate of change?
Well, it's changing at a certain rate over a certain period of time. So in this case, like I guess half a second, it's changing at that constant.
So are you looking at these blue horizontal lines here? You're saying these blue horizontal lines represent constant rates of change. Agree with that? What are we seeing on the left graph in general? Isabel?
I was going to say it's the approximate, well, the red line is the accumulation, is the rate of the accumulation, and the blue lines are the approximate constants for that. So
One more time, what was the function? Say it again?
that's the rate.
The red function is the rate of change, and then the blue,
Is the
approximate rate of change. Agree with that? Yep, you're getting lots of nods, okay? So yeah, so the red graph is the exact rate of change, and then the blue is approximating that rate of change with constant rates over half-second intervals, okay? Tell me something else that's going on here. Mary, anything you want?
The right graph is the piecewise linear graph formed from the approximate constant rates of change.
Okay.
And the right graph is accumulation.
All right, so exact or approximating?
Approximate.
Yeah. Did you hear all that she said there? It's really good. She said it was a piecewise linear function that came from the approximating rates that's building for us. One more time. What is it? giving us?
Approximate accumulation.
Approximate accumulation function. Good. Yeah. So that's our accumulated weight function. So we call it we could call it W of x, and this is R of W of x. Okay. What does the x-axis quantity represent? Joe? Time. For both graphs?
Yes.
Both graphs we got time increasing from 0 up to something like 2.5 here. Okay. What is the y quantity on the left-hand graph? Charles? What are we measuring here, the y quantity on the left-hand graph? Okay, which is what? Rate of change of the weight is the y-axis on this left-hand graph, right? And Nathan, what about the y-axis on this right-hand graph?
That's just a
Change of weight?
accumulated weight.
Accumulated weight, right? Accumulated weight. Okay. So now I'm gonna change this graph, and then you're gonna decide. So what am I doing to this, or what's going on here? Ready? So talk to the person next to you. 30 seconds. What just happened? What just happened? Okay, Crystal, what just happened?
The weights have changed, it's not like the change in the x are smaller.
Okay, changes in x are smaller. Okay, and what's the consequence of that? Savannah, what's the result of making the changes smaller?
It's more accurate.
What's it? What's more accurate? Accumulation is more accurate. Is this a curve? Nathan, what is it? What's going on?
It's like, to us it looks like a curve, but if you like zoom in, it's just a bunch of piecewise.
Okay, good. So if we zoomed in, we'd still have a bunch of little, we could say that we've made dx sufficiently small to have a very good estimate of the accumulated weight, right? Okay. So question. Between 1 and 2 seconds elapsed, is the weight increasing or decreasing? How is it seen in the left graph? How is it seen in the right graph? So here's one, from 1 to 2 seconds. Talk to your neighbor. So how is the weight increasing or decreasing? How is that shown in the left graph? How is that shown in the right graph? Go.
Yeah, so on the right it's going up, but in the left-hand graph it's still positive.
Say that again, Roman. Say that again. What you just said.
For the right one, you can tell it's increasing because it's still going up, but for the left-hand graph, since it's a rate of change function and it's still positive, it's still increasing, it's just increasing at a slower rate.
Okay. I think you said you missed your right and left when you said it, so I was just checking to make sure. Yeah. You had it. So, what's that? Everyone, right? So, Kim, is it the weight increasing or decreasing? Increasing. Pick your graph. So you want to do left? Do you want to say y on the left graph or the right graph? You pick. Tell me, why does the left graph show us that the weight is increasing? How does it show?
Because the rate of change is still positive, so, but when it's decreasing on the left graph, that means that it's starting to level off and then to change between positive and negative.
Okay, so you went above and beyond. So the reason that it's increasing is simply because the left graph is positive, right? All those values between 1 and 2, the rate is positive. As long as the rate is positive, the weight will increase. Kirsten, how does the right graph show us that the weight is increasing?
It's still increasing?
Yeah,
Just
between
it
1 and 2.
And then when it stops, like going up as fast, it just
But just in general, how do we see the weight increasing from 1 to 2? How does the graph show us that the weight is increasing? Yeah, because it goes up. Exactly, because it goes up, right? Because the y values keep going up. The weight is increasing. Does So the y values are going up over that interval, exactly. Okay, so now both of you you're talking about something a little more advanced, and now we want to talk about that. So here, if the function is increasing, then its derivative is positive. Now, this is our function. If the function is decreasing, then its derivative is negative, okay? So the derivative of the rate here, or the rate of change of the rate, or the second derivative, would be what between 1 and 2? Negative, because this is decreasing. So what does a negative second derivative, suppose we're over here, we're graphing the second derivative. How does a negative second derivative show up in the original function? This is review now. How does a negative second derivative show up, Ben?
Is increasing at a slower rate or decreasing at a greater rate?
No, only the first one. It's
If the original function would be accumulating at a slower rate, or it's decreasing at a greater rate.
Okay, you're right. Okay, but which do we have? Right.
In this one, it's increasing slower.
Yes, so it's increasing at a slower rate. So what does it mean for the way the graph looks? Will? Concave down, right? So concave down is when we have the rates decreasing. The rates are decreasing. Rates are decreasing. And that would show up in our second derivative as second derivative being negative, below the x-axis, right? If we were to graph it. So from 1 to 2, we know that the second derivative would be below the x-axis negative. Means this is decreasing. Means our slope is decreasing. And that forms a concave down shape, right? Okay, so now, between 0.5 and 1.5. So from there to there, how can the change in weight, so in that 1 second increment, there's a change in weight, how can it be represented using the rate function? How can it be represented using the weight function? Everyone think for themselves? See, everyone should be able to write this down. This is like mini quiz. How can we represent that change in weight using the rate function? How can we represent the change in weight using the W function? Everyone see if you can write it down. All should be able to do this. So here we have the assumption everything's exact. We have exact rate function and exact accumulation, okay? So using the exact rate function, represent the change in weight. Using the weight function, represent the change in weight. Everyone do it. Okay, then compare with the person next to you. See if you got the same thing. Okay, Christy, you're up. Take your pick. Either one. I'll let you choose. Want to use this one? Tell me. This one over here is an integral? We want just the change in weight between 0.5 and 1.5? If you want to do integral, integral's over here. Nick. Oh, okay, integral? 0.5. Agree? That's what it is. We spent, right? So we spent the whole first month and a half building up that expression as our accumulation from rate. Accumulation from rate. Okay, right side, Dalton. How can I express the change in weight using that? So from 0.5 to 1.5. So we've got the weight function, we want a change in weight. We want the change in weight accumulated from 0.5 to 1.5. Kelvin.
W of 1.5 minus W of 0.5.
So the accumulated weight in the first 1.5 seconds minus what we accumulated in the first half second. Okay, so how are these two expressions related? LJ, how does that expression there relate to this one here?
The first expression is like represents like the little bits of
Okay.
change, and then the one is like the cumulative change minus like the first part of the change. If that makes sense.
Okay, so does this give us a number?
Uh,
Does it give us a number? A value?
Yes.
Yes. What about that? Does it give us a value?
Yeah.
How are they related? Roman, Calvin.
They're the same thing.
Sorry.
One is,
Like my heart.
the left side is just the open form. And
Okay.
the right side is the closed form.
Open form and closed form. Okay. And the numbers are? Same. Okay. In the last week now, or the last week and a half, we've been talking about then getting a closed form for the accumulation function. So knowing the rate function, having a closed form for the accumulated, for the weight function. Okay, so this represents a very complex and long process of adding up a zillion bits of weight, right? This, having a closed form of a weight function, is a very simple and quick calculation to get that exact same number that comes about from that very complicated calculation and process. Anybody have a question? Does it make sense? Okay, this is the fundamental theorem of calculus. It's putting together everything we've done all semester. This is the fundamental theorem. Okay, so let f be any antiderivative of f, little f. Then the accumulation from A up to any point that we want. So this is like a roving stopping point. Accumulation of all the bits of change would be the same as the accumulation at the end minus how much we've accumulated up to the beginning. Both calculate the net change in the quantity from A to X. Or both give us a net change function, right? A net change function, accumulating from A up to any stopping point. So both are a net change function. And then, so now we're going to pick. We're going to pick an ending point. So pick, accumulate up to B. So this gives us the net change from A to B, and so does this, gives us the net change from A to B. Okay, it's worth saying. So this property has enabled generations of people to do calculus without understanding really anything. So this can be just turned into a set of problems to do. That when you see this, you do this, right? But we know a lot more than that. We spent all semester building this up, one step at a time, to really understand what is this saying. And now we know. So the previous screen was an example. Okay, so in graphing calculator, go ahead and open that up. So let's check this property out. So look at the first row. So in the first column here, we'll have a rate of change function. And so we want to just investigate this property. So right here, the integral from 2 to 5 RT dt, what does that mean? So the integral from 2 to 5 R of t dt. Tell the person next to you, take turns, what does that mean? Take turns telling the person next to you, what does that mean? Integral from 2 to 5 RT dt. Go. Okay, Adra, you're up.
It's the accumulation from 2 to 5 with the rate of RT, which is, I don't know what it is, and then,
Okay, so should the accumulation from 2 to 5 with a rate. So what is accumulating? So what is accumulating exactly? Little bits of change, and so what is accumulating? When you look at this, what exactly is accumulating? Jimin. Some function. And what do we know about that function?
the integral of the rate of change, which is R.
Okay, so you reverted just back to reading it. You just reverted to reading it. So what does it mean? What's that?
The function in relation to the rate
Okay.
is accumulating between 2 to 5.
Right. Okay. Yeah. So what's accumulating from 2 to 5 is some quantity. Some quantity. What? What do we know about that quantity? Ashlyn. So some quantity is accumulating from 2 to 5, and we know. What do we know about that quantity? We know the rate. So is this the accumulation of the rates? Is this the accumulation of the rates, Sam?
Yeah, from 2 to 5.
The accumulation of the rates from 2 to 5. Kim, shaking your head. Tell me.
It's the accumulation of the actual function from 2 to 5 and multiplying it by the rate of change.
Okay.
It's just the rate.
Yeah, so are we accumulating rates? This is really important. No, we're not. So we're not accumulating rates. We're accumulating a quantity that has this rate of change profile. Okay? So we're accumulating a quantity that has that rate of change profile. Okay? So in graphing calculator, we can have, as you see there, line 2 is doing that for us. Line 2 is doing that for us. So all we need to do is put the rate function in, so cosine 2x. And you see that line 2 will evaluate the rate of change evaluate the accumulation of the quantity from 2 to 5 with that rate of change, okay? And so what is that number? 0.1 106,391, and that's just an approximation. We're just taking that many decimal places. Okay, so now I looked on my math lab and saw that you're all experts at finding the basic antiderivatives. Did very well on the assignment. Okay, so we need a closed form antiderivative for cosine 2x. Patrick.
That would be
Sine 2x. So here's the rule from here on out. Whenever you take an antiderivative, check it. How can you check it? Take the derivative. Every single time that you do an antiderivative, take the derivative, and what should happen? Should be what you started with. Should be what you started with, okay? Being good at antiderivatives means knowing derivatives inside and out, knowing the derivative rules inside and out. So we need more practice taking derivatives. So every time we do an antiderivative, take the derivative. See if you get the original thing. If you don't, then you'll have an idea of how to adjust your first guess, okay? So is this the antiderivative? If we take the derivative of this, we get Sam.
It'd be cosine 2x times 2.
Cosine 2x times
So you
2.
need to divide sine 2x by 2.
So we need an adjustment to this so that when we're all said and done, there's no 2 there. Divide by 2, right? So it's great that we went for it, okay? And that's what you should do. Don't look at this and say, oh, I have no idea because it's confusing because there's a 2 there. Just go for it and then check. Take the derivative. We took the derivative and we saw we have this extra 2 that we don't want, right? What do we have to do to this first guess so that when we take the derivative, we'll get just what we want? Divide by 2. And then I'm going to add e cubed. Can I do that? Do we still have the antiderivative? Or an antiderivative? Yeah. So now let's put our function in graphing calculator in the third line. We're going to put it in. Sine 2x plus e cubed. And what did I forget? Divide by 2. So 0.5, I can multiply by 0.5. So it evaluated the open form from 2 to 5, and then we found an antiderivative, and we evaluated using that closed form. Did we get the same thing? Exactly the same. So this is quite powerful and amazing because this represents a long process of adding a zillion things together, which even takes a computer a long time. We can get that exact result very easily by just evaluating a function. And getting the output of the function, the difference of outputs of a function, gives us the same number of this very complicated long process that took us a month to understand. Okay? So this is really powerful to be able to have this, this principle, this property, in order to get a value that in essence is a very long and complicated process. We can do it very easily. So, check. So I want you guys to do the next 2 rows. Use graphing calculator, finish these 2 rows of the table. You can work together, okay? Okay, grab me if you have a question, okay?
What is
The second what? E to the function, rate function? E to the minus x plus x. E to the minus x plus x. Every time you take an antiderivative, what are you going to do?
Check it.
By? Take the derivative of it. And see if you got what you started with.
That's what, like, that's the real, like, E is always yeah. Okay, yeah, so that's
Put that in.
Oh, like 6
Remember, if you're not sure, just go for it. Get something close, and then take the derivative and see how you need to adjust your guess.
That's something.
yeah.
Think so.
That's right. It's just
You go on the right.
So with the constant root next to it.
It's negative one. Negative one.
just like in the homework, we had to find out the concept was.
Remember,
There's negative.
Grab me if you have a question. Any questions? You're stuck.
So that would be
No, it
negative.
works. no, it's negative one, it's negative e to the x. That should be.
Negative?
Oh, yeah, negative
Oh,
e
it
raised
is.
to negative x. Yeah.
Yeah, when you type this
So the angle would be negative.
Yeah.
Yeah. Because negative x, like the derivative of the negative x.
I got the parentheses.
Plus 1/2 x squared.
I'll just erase that one.
Put it, divided by.
Just call it the parentheses.
Negative e raised to negative x plus 1/2. I know it's right. Yeah.
So would it be 3 over
I
x?
was like, what? I was like, what is going on here? No, I'm right.
Would it be 3 over x squared plus x plus a plus 1?
3 divided by x.
So for that net change, as a open form, the net change of e to the minus x plus x from 2 to 5, I got 10.6286. Did you get that? Okay, so now we need the closed form antiderivative to do it the other way. Jerry, did you get the closed form antiderivative?
It's, negative e, negative e to x,
Negative e to the
negative x
negative x,
plus x squared over 2.
x squared over 2. Want to stop there? Yeah, plus 0. You know, you can do add 0 or add anything you want. Add 100, right? So we will put that in. Negative e. Get the same thing. Okay, last one, 3 over x plus 1. Let's see. Nicole, did you get that in graphing calculator, the open form?
Sorry, I'm working on the last one.
Oh, you're on the second one. Okay,
Sorry.
no problem. Will.
I got
5.7487? 887. Other people get that? Okay. Closed form antiderivative. Connor. So what function has this as its derivative?
It would be 3 ln x
Okay?
plus x.
It's not a t. How can you find out if it's right, Connor?
Plug it in.
Okay, so there's two ways we can find out this is right? One of the ways is
His derivative.
take the derivative just to see if that closed form is correct. And then we could also put it in for f and graphing calculator to see if the numbers match, right? The numbers match. Do they?
Yeah, that's right.
Okay. Anybody have a question? Okay, so some of you have had some calculus before. Notice that all semester long, those who have had calculus before, we have not said one thing about what Jack actually brought it up early in the semester. Those who've had calculus before. What have you learned that was about? Anyone? How many people have had calculus before? Oh, just a few. Okay, good. That's good. Okay, because what many emphasize is that this is about area, and note we haven't said anything about area. Okay, so and that can. If you get convinced that this is all about area, then that becomes kind of a stumbling block because you kind of get stuck on seeing areas. But it's not. We know what this is about now. All right? We know what this is about. Rate of change. It's about rate of change. Okay, some notation here. So this expression right here, we have a kind of a short form for it, a convenient way to write that. So if we don't want to calculate the actual value, but we want to express it, and we don't want to write out this difference, we can express it this way. So it's the function evaluated at b, and then evaluated at a and subtract. So this thing right here is another way to express this difference of accumulation values or antiderivative values. So you'll see, so it's the function, vertical bar, and then the final value of x on top and the initial value of x on bottom. Okay, we're going to do this on Wednesday as a review. And we're going to go here. Okay, this is just practice. Okay, so we want to make, here's something new. We want to make heads or tails of this. And so making heads or tails of this is really asking, what does it mean? So what does this mean? So reading it from left to right is valid, but it's not about what it means. So I can say the derivative with respect to x of the integral from 4 to 7 of sine of 3 cosine x dx. Okay, that's reading it, and that's correct. That's not what it means, okay? So with your partner, See what you can come up with. Now, I'm not asking you to evaluate it. I'm not saying what does it equal. I'm simply saying, what does that mean? Okay, go. See if you can talk it out.
Like, you remember, that's the equation.
We can't sleep, man.
Oh, yeah.
We don't have to stay up.
So if they take the mean,
Here's what's not allowed. Derivative, antiderivative, and integral. Okay? Those are not allowed in your phrase of what this means.
You can still change no, like I know, but I'm saying that you do want to say the change in accumulation. Yeah, before it's up. That's probably.
Anybody want to give it a shot? Kim,
Is it a rate of change?
rate of change.
For the rate of change? So is it the second rate of change function?
So it's the rate of change of a rate of change. Roman, agree with that?
I just noticed it had that thing there, so now my world got flipped upside down, so I gotta look at it again.
Oh, okay.
On the back.
Calvin.
I think it's the accumulation from 4 to 7 with that perspective rate. So,
Let's start from the beginning.
it's the accumulation.
It's an accumulation.
Yeah.
This is an accumulation. John. Rate of change. It's a rate of change, right? Because it's a rate of change. Okay. Okay. You want to try again?
It's the rate of change from 4 to 7.
It's not easy, so we gotta really remember what everything means. So it's the rate. Someone else had their hand up. Rate of change of Jimin.
It's the rate of change of the accumulation in respect to the rate of change sine 3 from 4 to 7.
From 4 to 7. Okay, that was fair. That's fair. Anyone else want to try? Savannah.
The rate of change of the accumulation from 4 to 7 of some function with the rate of change of sine 1
That was an improvement. Yeah. So that was an improvement. Did you hear what she said? One more. Do it again. Say it again.
The rate of change of the accumulation from 4 to 7 of some function with the rate of change of sine 3 cosine.
Okay. So now, what's that? So now let's talk about how would we evaluate that or get something that's equal to that. So maybe we should start with, let's just start with this accumulation. The accumulation from 4 to 7 of some quantity whose rate is this. What could we say about that? Just in general. Joe, what could we say about the accumulation from 4 to 7 of a quantity whose rate is this? Is there anything we could say?
I don't understand. Like, are you asking like for a specific number, or
Okay.
it gives you let's say a quantity that is the little bits of change that are added up between 4 and 7?
Okay. So yeah. So you're on the right track. So is it? Is it a number? You say yes. It's a number. Is it a number? Yuntong says yes. So then what are we asking for? We're asking for the rate of change of a number. What is that? Some are saying 0. Is it 0? Yeah, it's 0. Because this is the quantity. The accumulation from 4, starting at 4, ending at 7, given the rate of change function, is a known number. It's a value. And so if it's constant, what's the rate of change of a constant? 0. Okay, how about this? So now, have a discussion. What does it mean? And can we make some heads or tails about what it equals? So first, what does it mean? And then, what does it equal? Go.
Yeah.
Okay, Jeff, back to you. Any ideas?
Okay. So that is a rate of change.
Rate of change.
From 4 to x, and since x it can be any number, it's going to be a function.
Good. So now this thing is this a constant anymore? What is it? A function. What kind of function is it? You know what kind of function it is?
No, but it's a rate of change function.
It's a rate of change function. Agree with that, Ben? No? Was it?
Sine 3 cosine t is the rate of change.
Okay, that's a rate of change. But so this whole thing, so the whole integral expression, what kind is it? Accumulation function. Okay, so we got the rate of change of an accumulation function, specifically the one that starts at 4 and has rate sine 3 cosine t. How are we gonna? So is this 0? No, this is another function. So it's the rate of change of an accumulation function is a function. Okay, so how are we gonna make some progress on this one? So how about, can we just look at the integral expression? What does it equal? Just the integral expression. Sam, any idea?
Well, it would just be the accumulation of 4 to x of some function that's rate of change is sine 3 cosine.
Okay, so he said of some function whose rate is that. So can we just call that some function? Can we just call that f of t? Is it fair? So there's some function whose rate is that. So this capital F is what relative to that function? What do we call that, capital F? This is the rate of this one. That's the antiderivative, right? And so now what I put a box around, what does it equal if this is, we know, is our antiderivative? Yeah, so we can use this notation I just showed you. Isn't it this? Which is? Boom. So this is what I put a box around. It's an accumulation function starting at 4, and this is the closed form of it, right? This is the closed form. But what is the red box is asking for the derivative of that with respect to x. So we know the difference, or the derivative of a difference is just the difference of the derivatives. We know that. So what is the derivative of this accumulation function? 2 people know. I mean, I'm just saying, so are there more? So more who know what this is? 3, 4. So we got this accumulation function. What's the derivative of it? Go ahead, Joe.
Sine 3 cosine.
Yeah.
Cosine x.
This will be the rate of change of that accumulation function. Well, it's the rate we started with. Sine of 3 cosine x. What's the rate of change of that accumulation function evaluated at 4? 0. It's a constant. Is that what you're saying, Will? So this is the accumulation function for this rate, and now we're taking the rate of change of it. So it's that rate function. And then, but then we also have the starting at 4, but the rate of change of that constant is 0. So that function is just the original rate function we started with. Okay, but still, when you have columns like this, there can be variations, so you want to understand and be able to evaluate this process. Don't just see one that looks like, every time it looks like this, and just write this down, because it's not always the case. So go through the process every time and think about what's happening. Okay, so Wednesday is my math lab. This is the last material for the exam Thursday. Stuff we do Wednesday won't be on the exam. So we'll have another My Math Lab Wednesday morning. I've put up quizzes for your studying, and then I'm going to start loading up today I'll start loading up some other practice My Math Lab assignments, and then get you a review outline also, an outline of ideas and concepts. Any questions about the exam Thursday? So My Math Lab is due Wednesday. Jimin? I think so. I'll let you know.
Mark, can I ask a quick question?
Yeah, sure. Hold on, let me turn the video off here.